Hi, Mike.
Hi, so who are you and what are we doing in your office today?
I'm Juggs Ravalia. I own Windows CE device drivers and the framework associated with it. And today we'll look at what's new in device world for Windows CE 6.0.
Fantastic, let's get started. Okay, so today we're going to be talking about device drivers specifically. And it sounds like with the upcoming release of CE6
Right.
that there are a number of changes that occur for device drivers.
Absolutely.
What can you tell us about that?
So with Windows CE 5.0, most of the drivers were loaded either in device.exe or GUIs.exe, which were actually in user mode. Now with Windows CE 6.0, which you might know, we have the notion of unified kernel, where device.exe and GUIs.exe have actually vanished and become DLLs that are loaded in the kernel. And in fact, all your drivers by default are loaded by GUIs.dll or device.dll in the kernel. So that by itself is a huge change.
Okay. All right, so what does that mean for the device driver developer?
Right, so for the device driver developers, either you're writing your drivers from scratch or you already have been writing drivers and you need to port those drivers to Windows CE 6.0. So if you're porting your drivers, then there are three key areas that I would say you need to pay attention to. One is some of the APIs that we've deprecated, like map caller pointer. The Windows CE 6.0 new kernel virtual memory layout has changed, and due to that, some of the APIs don't actually make sense.
Right.
So those deprecated APIs, either you need to remove them or do something else, and I can dig deeper into those.
Okay, so you mentioned that a number of features of the operating system are moving from user space to kernel space, such as GUIs and file system manager, device driver manager, and so on.
Right.
So what does that mean for a device driver? You've also mentioned deprecated APIs. So things like setk mode and set proc permissions and that kind of stuff has gone away.
Absolutely.
So now how does a device driver touch memory?
So you're right. I said there were three things that you really need to be careful about. One was the deprecated APIs. Well, the second thing is how your driver is going to access the caller's buffer. With the new CE 6.0 virtual memory layout, the user processes do not have a fixed virtual memory layout. As the kernel switches between the processes, each process has a unique virtual memory user mode space mapping. Since that changes as you go from one process to another, and if your driver needs to access the caller's buffer asynchronously, then you go to marshal that buffer. So wherever the driver is trying to access the caller's buffer asynchronously, you'll need to make some modifications, because pointers only make sense for the process that they were actually created in. The moment another process has been swapped in, that pointer now would point to something totally different. So it's very critical that you have that buffer marshaled into the kernel. We have APIs for that, so that you can use the caller's buffer synchronously.
So could you just draw out the difference between the CE5 memory layout within the operating system and the CE6 so that we can see the difference?
Absolutely. That would be good. I think I'll pick blue.
Perfect.
Just to show you. So let's assume that this is my brain like a CPU, and I can always see 4 gigabytes of memory, virtual memory space. In the old days, we had 2 gigabyte where the kernel resides. I hope you can see my handwriting, but I'll try to make it as clear.
Yeah, I can see it.
Okay. Now I'll change my marker just to show that this 2 remaining gigabyte was where the user mode processes actually reside. So what happened in Windows CE 5.0 is that we had this first slot here. Remember, first of all, I should say that there were actually slots of 32 meg.
So the architecture of CE5
Right.
limited the number of running processes purely based on the VM layout of the operating system.
Absolutely. So if I say this is slot 0, slot 1, and these were my processes, device.exe, filesys.exe, and so on, I could have up to 32 processes.
Each with 32 meg virtual address space.
Each with 32 virtual memory address space. So if my brain can perceive this 4 gigabyte of virtual memory space, it's very important to see that I could address each and every process at a given time. I could know exactly if I had a pointer, let's suppose in files is pointing to this location, and it pointed to, let's say, an object here, which was green in color, whether it's the other process running, or it was device.exe, or for example, a user application like a traffic app running, that pointer actually always pointed to the green object I've drawn. It didn't matter which was the current process running.
Right, because it's a fixed pointer inside of that 2 gig user space.
Absolutely, you got it. It's more like this building is divided into multiple chunks.
Right.
And all the buildings, blocks, are always there.
Okay.
So that's why we had 32 process limit, and every process could only have 32 megs of virtual memory space.
Right.
So you could actually hit a virtual memory error before running out of actual physical memory.
Okay. Okay. So what about CE6?
So I think I'll drop this and take you to C6.
Sure.
So if you go to C6.0, this changes, but this changes drastically here. So the upper part of it, of course my brain is still the same, so I can still only perceive 4 gigabytes. But we've changed the layout in this way. So let's go one level back and say that this is my brain, it's perceiving this building. My kernel is always 2 gigabyte. That's fixed mapping. That never changes as you go from one process to another. But every process now has 2 gigabyte of virtual memory space. Of course, there's fine division within this. There's shared heap up here. There is the user mode, user space, virtual memory, and so on. It's divided. But as you switch processes, what happens is this building now is actually being created by having the kernel and one other process. It could be this process, or it could be another process. So I'll call this A.exe or B.exe. So now your building is created having the kernel and A.exe, and that's what you can access at any given time. Or it can be created by kernel and B.exe to form the 4 gigabytes that you can address.
Right.
Therefore,
So that means that a pointer that lives inside of process A.
right, so now let's go back. Let's say this was my pointer pointing to the green object. If now I'm in the kernel and I'm trying to access this pointer, and this is my kernel driver, if I have this pointer pointing here, and now all of a sudden process B becomes the active process, I'll be pointing to something totally different, none other than the green object here. It would actually be nothing possibly, or it could be something orange for all I care. So that's why you need to make sure that you marshal this buffer when you're trying to access the buffer asynchronously.
Right. So how do you do that? What's the API that you use to marshal that?
So when you want to marshal a pointer, you go to call CE alloc asynchronous buffer.
And what's calling that? The user process.
So no, so your driver
Or
is the
so the
only
driver.
person knows whether you want to access the buffer synchronously or asynchronously.
Right.
When you need to access this buffer synchronously, you go to call CE alloc asynchronous buffer. There's something I really need to point out here that's really, really critical. So this is the important thing where I think I need to address the notion of synchronous or asynchronous. Let's say this is the kernel driver, and you have a second thread. That's the driver's thread, usually let's say an IST, which is an interrupt service thread. So what happens is, if the caller makes a call, so let's say this call from a user app goes to the kernel driver with the buffer here,
Yeah.
and the thread here, let's say, is waiting on a single object.
Mm-hmm.
And then the driver tells the IST to process this buffer,
Yep.
and then returns this thread back.
Yep.
From the user application, you might say this is synchronous. I waited, whatever I wanted was actually processed, and then the call returned.
Sure.
But in terms of porting, this falls into the asynchronous arena. By asynchronous, it means that you're trying to access the caller's buffer on a second thread and not on the caller's thread.
Okay.
That's the most important part. So in this case, your driver will also call CE alloc asynchronous buffer. What that will do is it will try to marshal this buffer across into the kernel's virtual memory address space. And now, guess what? Everything that your second IST thread is going to access will be local, so that as you swap all the other processes, your pointer always makes sense and always addresses the same buffer that you wanted.
Okay, so what does an application developer need to know or do about this? So I allocate a buffer.
Right.
I'm going to maybe have a device driver that's running in kernel mode.
Absolutely.
Fill that buffer with some data.
That's right.
So maybe I call something like local alloc to allocate a buffer.
Right.
And then I somehow pass that
it via
buffer
device out of
pointer.
control.
Right.
Yes,
So
yes.
then what happens?
So when you call with that pointer, the driver there does three basic things when you're porting. One of them is to access check. We want to make sure that your drivers are in kernel, so security is a very important thing. We don't want to compromise the entire kernel because of a poorly written driver.
Right.
So the first thing that we actually, not even say as a best practice, but we recommend strongly, is to access check the pointer. And by access check is verifying that the caller has the right privilege to access the buffer addressed by the pointer that's the user is pointing to. I will give you a good example. The kernel here have access to entire memory.
Sure.
So it has the gun. If the user points the gun and says, go and corrupt this memory, the kernel can actually do this. So it is my right, and it is something as a good practice for me to check, does that caller have access to that buffer? If it doesn't, I should return that call right away. And for that, we have an API. That API is called CE Open Caller Buffer. So if the user application passed you a pointer pointing to a kernel memory, you would actually reject that because you don't want to modify kernel memory on behalf of the users.
Sure.
So you'd call CE Open Caller Buffer, and you'd have access check the buffer. The second thing you would do is you'd say if it's an input buffer, because the user application can actually modify the buffer asynchronously. So I access check. But if I access check and then on a second thread he asynchronously modifies the buffer, then I might be actually using wrong input values than what I thought initially when I access checked. So if you don't own the user app and you're going to support any third-party application to talk to your driver, even before you do CE Open Caller Buffer, you want to call CE alloc duplicate buffer. What CE alloc duplicate buffer does is actually duplicates the buffer before you access check it. The moment you duplicate the buffer, you have your own buffer that the caller cannot actually asynchronously modify it. Since the caller cannot asynchronously modify this buffer, you access check your local buffer, you party on your local buffers before you return. If it happens that you're going to access the caller's buffer asynchronously here means two things. Either on a second thread, or even after you've returned the call, you still need to access that buffer. That's also asynchronous. You need to call CE alloc asynchronous buffer. Of course, you're wondering that now I have the buffer here, what do I do with that buffer?
Sure.
So once you've modified and you've played with the data, for you to return the data back, we have an API called CE free asynchronous buffer.
So all of this is completely transparent to the application. The application
all
has.
of this is absolutely transparent to the application. Absolutely, you got that right.
So the application developer has no clue and doesn't even have to know how this stuff works.
Absolutely. The application developer will make the same calls that they did in Windows CE 5.0, and they should just work.
Right.
Absolutely.
Perfect. So one of the things you're talking about here is device drivers in the kernel.
Right.
But I know for sure that also on CE6 we have user mode device drivers.
Oh, that's a very, very good question. It seems
So-
like you've been playing a lot with Windows CE 6.0.
Believe it.
Right.
So what's the difference between a user mode driver and a kernel mode driver? And in fact, why do we even have two different driver models?
So, from Windows CE 5.0, where we had drivers in user mode, we brought all the drivers in kernel mode. But then we went back and said, OEMs are trying to write some drivers, but absolutely they're not going to have all the drivers written by themselves. They've not tested all the drivers thoroughly. There's some drivers that are not performance critical, like an SDI or GPS driver, to take an example. So we said, let's give them a user mode framework for three key reasons. One is improved stability. By improved stability, I mean that you're trying to isolate the driver from the kernel. and you're trying to isolate one driver from other drivers because you can have multiple user mode driver host processes.
So on CE5 we had one device driver manager, device.exe.
Absolutely.
So on CE6
you can have multiple.
Let's ask this first. In the kernel, what is the driver manager in the kernel?
Device.dll, because it's a DLL just loaded by the kernel.
Okay. And there is just one instance of device.dll within the kernel?
Absolutely.
Okay. So why do we only have one instance of device.dll in the kernel, but the support for multiple instances of, I guess it's called udevice.exe
So
in
as
user
I was
space?
trying to say, the first point is improve stability. You might give me a driver and another guy might give me a driver. I don't want you to stamp on each other's heap. So what do? I separate you into different user mode processes. So you run in udevice.exe and he runs on udevice.exe. But both of you are two separate exes. One crashing does not bother the other person and the other person crashing doesn't bother the first.
Okay.
So we separate them across the board.
So why not do the same for the kernel? Why don't we have multiple instances of device.dll in the kernel?
Because all of them would still have access to the entire kernel heap. Everything in the kernel can touch anything that the other kernel components are actually touching. You can actually go and step on someone else's heap there. There is no differentiation unless you have multiple nk.exes, which means you have multiple kernels. So it's just absolutely the same as having udevice.exe, only that whatever is in the kernel can access kernel mode APIs. They're very performant, they need to be high performant, and they're critical to the system, and you've tested them well.
So give me an example of a device driver that lives in the kernel that needs to be high performance.
A very good example would be NDIS drivers, networking NDIS miniport drivers. So networking drivers, for example, whenever you're doing Wi-Fi or something, you need high speed, and because they're performant, they happen to reside in the kernel. A second example is file sys. Because you're writing so much data back and forth to the file system is another example of a very good driver that resides in the kernel.
Okay. So would it be a fair statement to say that device drivers that live in the kernel are typically put there by the OEM, the person that's building a system?
Right.
And then device drivers that live in user space may well be third-party device drivers?
Absolutely, that's correct.
Would you see in some circumstances that third-party device drivers may also be loaded into the kernel?
So third-party device drivers, if they're loaded in the kernel, then the OEM has actually selected that I'm going to run this driver in the kernel. He's passed some of the tests that make sure that it's stable and up to an acceptable bar. So I think we're giving a lot of flexibility here to the OEMs to choose where to load the drivers. But if you have a third-party driver where, let's say, I already have an embedded device, and then I'm going to purchase a third-party driver like an SDIO GPS, then that driver, we want the driver to be loaded in user mode, and we would want the OEMs to support us so that those drivers get loaded into the user mode.
Okay, so I'm a device driver developer. I want to write a device driver.
Right.
How much do I need to know, or how much do I need to code differently if I'm building a user mode driver versus a kernel mode driver?
Right. I think, Mike, you should have been during our design, so you have a lot of input here. So the first goal when we were trying to design the user mode driver framework was to say that you can actually move your driver between kernel and user space without any change.
Uh-huh.
We wanted no change. We wanted everything to be completely agnostic to the user application as well as the parent bus driver. It would not know where the driver is. However, there are a few security implications that prevent us from you having your kernel driver just work the same way as in user mode. Some drivers can actually work in user mode and kernel, and you can shift them if they don't use a few of the things that I can go details into.
Sure, let's do that.
One of the things is embedded pointers. So I guess I'll show you how the embedded pointer problem is. So I think I can still use my diagram here. I like this diagram. So let's suppose this is our famous udevice.exe, which is actually a user mode driver host. You can have multiple udevice.exe, and each udevice.exe can house multiple user mode drivers.
Or a single driver.
Or a single driver, absolutely. Or a single driver, you're
So
right.
before you carry on, how do I, if I'm building a device driver, how do I notify the system that my device driver either needs to be blocked in with other DLLs, other drivers, or needs to be hosted in its own unique instance of udevice.exe?
Absolutely. I like your questions, the way you're stepping one by one. So yes, so when you have your driver, you have your keys. So if you go to HKLN,
Oh, so it's done by the registry key.
it's done by registry key.
Okay.
Absolutely. So we have registry keys, and we have a registry key that you say that set the user proc group to be X, and all the DLLs drivers that are in X will be loaded in one user mode process. If you don't provide one, we'll always launch you in a separate one.
Okay, so the default action is to launch a unique instance of udevice.exe.
Absolutely, yes.
Right. But on your original CE5 diagram, I noticed that there are only 32 process slots.
Right.
So on CE6, am I still limited in the same way?
Right, so you don't have the limitation of 32 processes. You can go up to 32,000 processes theoretically.
Right.
But of course, you've got practical limits as well. Launching a process has a hit. It has a hit of 5 pages, which is like 20K. But that's more or less the same hit we had in CE 5.0. So even though we don't want you to launch as many as we want you to launch as few as you potentially can, there's a trade-off between how much memory hit you want to give the system and how much stability you want to earn. So of course we want OEMs to gauge that rather than just launching every driver into separate udevice.exe.
Okay, so having multiple udevices.exe is really not that much of a hit on CE6 then?
It's not so much of a hit, absolutely.
Right. Okay, so proceed with your embedded pointer.
Absolutely.
discussion.
Back to the discussion. Can I move my user mode driver and kernel mode driver back and forth? Yes, only in a few cases. The first one is the embedded pointer. So I'll go back to my original diagram, rub a few things, leave most of it. You've got to love the markers here, but various colors. So I'll pick the brown one. So let's say again, you have your kernel driver here. Now you move your kernel driver and it's now loaded in udevice.
Do any of the interfaces on the driver need to change? Any of the exposed interfaces on the driver need to change between user mode and kernel space?
Absolutely no.
Okay.
The interfaces remain exactly the same. So to the user application, we want it to be completely agnostic.
And is there a limit to the type of device drivers that can be kernel or can be user mode?
So there are a few limitations, and I'm going to go through those limitations. As I said, there are 4 things. One of the limitations...
What I meant was driver type. So can a display driver be both? Can a
Oh.
networking driver be both? Can a USB driver be both?
Right. I think I got it. So for you to have your driver ported to user mode driver process, we've got to support it. We've got to support it either in our USB-D, which is our USB bus, or we've got to either have, for example, NDIS. For example, if you have an NDIS miniport driver, you're tightly linking with NDIS.lib and the NDIS.h header. So what happens here is that if you move your driver, an NDIS miniport driver, to user mode, now you go to access the functionality across processes. So NDIS itself has to open up the architecture via some IO controls, which are custom IO controls, or some PSLs, so that the user mode driver can now access that functionality across the board. Today we have not done that for USB, neither have we done for NDIS. But you can port your SD drivers, you can port your serial drivers. We will be making more and more buses open.
So that
for you
means
to
that
port.
USB and NDIS must be kernel mode.
Absolutely, yes.
Okay. So one other question.
Okay.
While I think about it,
Gotcha.
and we'll unwind our stack in just a few seconds.
No problem.
So the question is, by default, is a driver user mode or kernel mode?
By default, it's kernel mode.
Okay, so I need to do this additional registry work to make it...
You go to do a registry
Okay.
word and set it as dev flag stand for you, for device manager to know that we've got to load this in user mode.
Okay, perfect.
Absolutely.
Okay, so we have our user mode driver.
So we have our user mode driver. So now, let's assume this is gone. We have a buffer here. So you have a kernel module. I think I missed one thing. While I was going through 3 things that user mode drivers, kernel mode drivers would have to know when porting.
Yeah.
There was 2 things that I said: asynchronous access, and I also talked about deprecated APIs. But there's one more thing: you cannot show any user interface in the kernel anymore.
Of course, well that makes sense, right?
Right. So what happens is, whenever you're supposed to show UI, we've given you another call. It's called CE call user proc. What you do is you call this API, and you have to code up your own DLL, mydll.dll. You export a certain interface, and you pass some input and output buffers. And what will happen is it will marshal the call through to a user mode driver that we've implemented. It's called UI proxy.dll. And it will show you UI in user mode for you if you're in the kernel. So that's a good example of a call originating from the kernel to the user mode driver.
And that can be any DLL, just a regular Win32 C++ DLL.
Absolutely, you got that right.
Right.
So that is just an example how a kernel module makes a call to user mode process. So let's look at that in detail.
Can a user mode device driver still call user proc?
Absolutely. So that's where the entire, I would say, the entire beauty of the framework comes up. When you call call user proc, in core DLL where we thump the call, we actually have an if def. So if it is core DLL, then we actually launch it in user process and we do user mode driver framework stuff. But if it is in the caller process, that means it's in the user space, then we'll just load in proc. So we'll do load library on the DLL that you've called it.
Huh, that's neat.
So now you'll just have the DLL inside you. You can just load it and you can do all your UI stuff.
That's very neat.
Good question. And I can show you another example of that yet in details when we go further.
Okay, perfect.
So I'll go rewind back to my 4 limitations. It's good that we've jumped all the way, covered all of the statics and come back.
Yeah.
Very good. So now, let's say I am this kernel process. I want to make a call to the user mode driver. I have this buffer. So I'm going to bring in the notion of reflector here. We can go that in detail.
Okay.
But basically we have device manager here, and for every user mode driver there is an instance of the reflector object. What this reflector object does is that it marshals first level parameters to the user mode driver's virtual memory space. So when you call call user proc, or for that matter any other APIs to the user mode driver, any interface that it exposes, the reflector, let's assume this is the reflector. I don't know whether that color is really good, but
so what is the reflector?
okay. So the first thing that an application would do to load a device would be activate device or activate device EX. When that call is made, the device manager will say, is this driver supposed to be loaded in user mode using the registry keys? If it happens that it needs to be loaded in user mode, I'll look a few keys and I will instantiate an object of the reflector. What the reflector does is that it actually acts as a proxy to carry out kernel level actions on behalf of the user mode driver.
Okay.
So it is actually the nucleus of the entire user mode framework. So it takes all the requests from the device manager, marshals all the buffer, marshals the first level parameters across to the user mode driver space, and unmarshals all the results back all the way to the application.
Okay.
It's also one important thing about the reflector which I need to make a strong point here is that it does a lot of security checks. So when a user mode driver asks for any kernel level privilege, because it launched that user mode process, it knows exactly what it manages, what it launched. So it can tell you whether you're a valid person or not.
Okay.
So let's suppose that this call is made, the reflector has marshaled.
So is the reflector a process or DLL living in kernel space? Is it a unique thing?
Yes, absolutely. That's phenomenal because the reflector is actually just an object within device.dll. So it's not another DLL. It's just an object within our device.dll framework.
Okay.
So it completely becomes isolated from the end application or the driver's perspective.
Mm-hmm.
So let's assume this is the buffer, and this buffer is being marshaled into this udevice.exe. So everything works fine so long as that buffer has been marshaled and the user mode driver just accesses it and it returns back, no problem. But guess what? Let's assume that this has an embedded pointer. And the embedded pointer, of course, will be pointing to some other buffer there. Now what happens is the reflector has no notion what those 4 bytes of pointer mean. It could be D word, it could be a memory blob, it could be anything.
Mm-hmm.
So when it marshals these 4 bytes, when they're in this buffer, they haven't changed. They still point to this memory location.
Because there's nothing that marks that as being a pointer.
Absolutely. The reflector has no idea that it needs to marshal that buffer pointed by those 4 bytes. There is nothing that tells the reflector there is an embedded pointer stuck inside this memory block. So now when the user mode driver tries to reference the address, the embedded pointer, the buffer points to the kernel, and this is a security violation. We don't allow user mode space to access kernel memory. So this is where, if you have your user mode driver trying to access embedded pointers, you need to do work. So what would you do in this case? This is what you do. You take this buffer and add it to the end of the initial buffer. Change this embedded pointer to be an offset within this whole structure. And now call the user mode driver with the entire bigger memory block. The reflector would marshal all that. You've got all the data that you need locally. Now your embedded pointer is actually an offset to the embedded address, and the user mode driver will now have to treat the embedded pointer as an offset within that structure.
Mm-hmm.
This is how the desktop side works. The desktop side, actually, you go to flatten all your structures, and the driver always unflattens them or uses the embedded as offsets.
Right.
So this is something that there is one good thing we're going to do. The good thing is we're going to give you 2 APIs to flatten and unflatten. Today, we have not yet done this. So you as a driver developer have got to do this.
Okay. So you mentioned the desktop there. On the desktop, it looks like the desktop is moving away from kernel mode drivers and implementing user mode drivers.
Absolutely. Yes.
Whereas we're doing the opposite. We already had user mode drivers, now we're implementing kernel mode drivers.
Right.
So why is that?
So first and foremost, with the just Windows C 6.0 virtual memory layout change that we did, the notion of unified kernel so that all the other processes that are critical to the system move into kernel, where you'd have certain key drivers, even on the desktop side, there are 3 key drivers that will not move to user mode. Those include the networking, the file sys, and the video. So those drivers would remain in kernel mode, and others will move into user mode so that they don't compromise the system. So the first step that we have done is to move drivers by default to kernel, provide a user mode framework, and with next releases you will see more and more drivers, more and more frameworks will be doing to move drivers to user space. So we'll also be leading towards that step, absolutely.
Right, okay.
So this is one thing where you need to do a change to move to user mode processes, correct?
Okay. Mm-hmm.
There's another thing. The second thing is, let's assume your driver is calling certain kernel mode only APIs. Then you cannot move that driver to user mode.
Do you have an example of an API that's kernel mode only?
Right, so I would give you a good example. So if you call virtual alloc EX, we as from a driver framework team, we don't think that virtual alloc EX needs to be called by a driver. So only the kernel is allowed to call that, to allocate a buffer across the 2 processes. So let me give you a good example. We went how we tackle this problem. So with Windows C 6.0, we have certain APIs. I think Mike can still see some of it.
Yeah, that's fine.
So we went through a list of all the APIs that are only called or only exposed in the kernel and not in the user mode. So I'll give you a good example. So let's take virtual alloc and let's take virtual alloc EX. By the way, we'll have a good documentation on all these APIs. So we say, what are some of the APIs that drivers have to call to get their functionality obtained? So virtual alloc, you need to map physical memory, you need to map hardware memory. So we say, yes, we know that virtual alloc is something drivers will call. So if you look at core DLL that has virtual alloc, you'll also see the beauty of the framework again, where you say if k core DLL, and the else part. So what happens is, if it is in k core DLL, you can actually call virtual copy as it is, and will just work. But if you're in user mode, if you're just any other user mode application, it will fail. But how does it fail for a user mode application and not a user mode driver? This is the key. So in the else part, you'll always see that there will be a check done by the reflector that I was talking to you about to make sure that it knows the process ID of the user mode driver making this call. And then secondly, it will take this particular call and make a device IO control call to the reflector.
So does that mean that when a user mode device driver host is created,
Right.
it's actually the kernel space device driver manager that's launching that new instance of udevice.exe?
Absolutely.
Which is why it knows the process ID of
Absolutely. So what the device manager is doing is it creates a reflector object within device.dll and saying, you own this guy. You launch it, you manage it. You've got to know everything about him.
that. Right.
And that's why he's the guard about that driver. When that driver gets unloaded and says that there are no more drivers, it will actually be responsible for exiting the udevice.exe process as well.
Okay.
So what will happen is there will be an IO control call with the custom IO control that the reflector understands. For this example, it could be reflector virtual copy. Of course, you're never going to call this, but this is all agnostic to you as a driver developer. Your driver calls virtual copy in kernel, it takes this route of implementation and gets the work done. You move the same driver to the user mode, you don't change anything, you still call virtual alloc, it comes to this part. I can show you a diagram of how this works to show you more in details. So let's assume that this is the user and this is the kernel boundary. So you have your user process, hello.exe, it makes a call. In the kernel you have your device manager, and it's talking to the reflector object. Remember that all this is within device.dll, and what the reflector has done is it's launched. I'll make it darker for you, Mike.
That's fine. I can see it. Launched an instance of udevice.exe.
Absolutely, with the user mode driver sitting in there. So, when the user mode makes this call, the call gets thumbed through the reflector to the reflector. The reflector knows, okay, I need to call this virtual copy on behalf of this. After doing the security checks, make sure it's physical memory, does the virtual copy because it resides in the kernel. It can do anything on behalf of the user mode driver so long as it's a valid call, so long as we've done the right security calls, so long as we've accepted that call to go through. And it will return back all the data resulting from that call back to the uDevice's address space so that the user mode driver can now access that buffer. Now if you look at virtual alloc EX, then this part doesn't exist at all. It only works in the kernel. So what happens is it's only in k-core-dll, you make virtual alloc EX and it will fail right away. We just won't support it. So that was the second part. If your drivers are going to make kernel only API calls, then you can't move it to user mode space.
Okay.
The third thing, very important, I think you also somehow brought this into the picture, but I'll address it. So let's take example of USB because I think it's a pretty common technology. So you have USB host controller, which could be OHCI, EHCI, UHCI, and you have your bus, and you have your user mode class driver. So of course we've not yet opened this, we've done this for SD technology, but let's assume that your USB class driver is in user space. Because your USB class driver is in user space, all the callbacks happen from USB D, which is the bus driver, to the user space. This is valid. The kernel can do a callback to the class driver. Now, let's take an example where you move USB D to user space. But then, oops, your class driver is actually in the kernel space. Now, USB-D being the bus driver cannot call back into the kernel. So, if you're going to move a bus driver, then you have to move the class driver with it to user space. You cannot have a dependency where you'll have a callback from user mode to kernel. So in this particular instance, what happens is having USB-D in user spaces forced you to have the USB class driver in user space as well.
Right.
So that's where those are the three things that you need to be careful about.
Okay.
There is one other point if you're using installable ISRs. Installable ISRs usually run in the kernel. What happens is if your user mode driver is going to modify that functionality, then we don't allow you any custom way of doing it, because usually in Windows CE 5.0 they would use shared memory between the kernel and user. Because they had access, you could actually do set K mode, which you were very familiar with, and access kernel memory.
Indeed.
Well, we now have blocked that. We don't want to leave any windows open like that. But we don't restrict you. We still want to make sure you can do the work that you need to do. So you can use GISR, which is our generic installable ISR, to install your ISR. Why? Is because the reflector knows all the interfaces of GISR, and when you make those calls, like in your user mode space, if you're in the kernel, the call is made directly. If you're in the user mode, they'll go to the reflector, they'll do the right security check, and the reflector will do the valid things for you after access checking the buffers.
Okay.
So those are the things that make sure that you need to do changes. But if your driver is not dealing with ISRs, if your driver is not dealing with embedded pointers, and you don't need to do any callbacks, then you can just move your driver back and forth, like our serial driver today that we move back and forth between kernel and user.
Okay. So assuming that today I've got a CE5 driver,
Right.
and I want to move that to CE6.
Right.
Of course I want to do that.
Right.
How long is that going to take to move a fairly kind of standard driver from CE5 to 6?
Right. So if you're familiar with all our documentation, it should take you less than an hour. But of course, I'm saying that if you're going to go through all the details, it shouldn't take you more than a day. If you have any other problems, Mike, you can please write to me, and I'll be more than helpful to sit down with you on that.
Okay.
Right. So I think we've also written a tool. I
Uh-huh.
think you've used this, the C App Compact. And if you run it on a driver, for example, it will tell you whether you're using some APIs that we've deprecated, the kernel mode only, and what changes you need to do and stuff like that.
Yes. In fact, I'm hoping to capture a demo of that at some other time.
Good. Good. Excellent.
Great. Well, I think this is a really good starting point for people to get to know what's new or different with CE6 drivers.